1.3, evaluating limits algebraically. So now we're to the part where we actually just get to do the algebra to find the limits. So the techniques for doing them algebraically are just directly substituting in whatever x value we're approaching. That's the easiest. Sometimes we have to factor or divide out in order to be able to do the limit. Other times we're going to have to rationalize. And there's another technique which I won't cover just yet because you need to learn how to do derivatives, which is the next big thing in this class. And that's L'Hopital's rule. So example 1, evaluating using direct substitution. So for example, or part A, we have the limit of 3 as x approaches 2. Now, 3 is a function, right? But it is a straight line. And 1, 2, 3, right? So this, ooh, huh, not that. This is y equals 3. Well, look at it. It doesn't matter what the x value is. No matter what x value I have, it's always going to be 3. So this is a constant, right? And like I said, for x equals 2, it's going to equal 3. But for x equals 5, it's going to be 3. For x equals negative 2, it's still going to be 3. So my limit, no matter what, is going to be 3. So you might want to make a note. Whenever you're taking the limit of a constant, and this is a constant because it is not an actual equation, it's a constant, then the limit is just going to be it. Another way that I like to look at this is, look at it, 3. Is there any x there? No, there's no x. Do I have something to plug my x into? No, because it's just the number 3. So the answer is just what it is. The constant itself is 3. And then b is just as simple as pi. The limit of x as x approaches negative 4. I do have something to plug in my x into. I have an x, so it is negative 4. Okay, example 2, evaluate using direct substitution. Again, but these are a little more, or well, they're just a little more. For part A, this is just simple direct substitution. And I am going to sit here and I'm going to plug in that 2. So 2 squared times the 4 plus 3. So I have 4 times 4 plus 3, so 16 plus 3, so 19. And there's my limit. For part B, usually, okay, well this is a rational function. It's a rational function because it's basically a function divided by another function. I like to highlight the word ratio, right? A ratio, if you remember. Oh, I don't know if you can see that. But a ratio is basically something over something, right? Okay, so for these, they start getting tricky. You have to make sure that if you were to plug in your x value, it's not going to make a 0 in the denominator. And here, when I plug in 1 into the denominator, it's 1 plus 1, so that's okay. But this would be a problem if it was 1 minus 1, and we'll see that in the next, or in a few examples ahead. Alright, so plug in 1. So 1 squared plus 1 plus 2 over 1 plus 1. So I have 1 plus 1 plus 2 over 2. So I have 4 over 2, so then I have just 2. Direct substitution, when it's just simple functions, it's just easy as pie. Alright, example 3, assume that the limit of f of x as x approaches 5 is 7, and the limit of g of x as x approaches 5 is negative 3. So notice, no equations. Okay, we don't have any equations here at all whatsoever. And you should be able to do this the same way. They're already telling you what the function's limit is as it approaches whatever x value. You're just going to use the actual numerical values. So you're going to use the 7 and the negative 3 to answer the following questions. So these are properties basically of limits. So for part A, they're telling us that the limit and of f of x plus 3 times g of x as x approaches 5, that's what we're looking for. So look at this like in a splitting up fashion. So as I was saying, split it up. Look at this as you're doing the limit of f of x as x approaches 5, which, if you recall, in the directions they told you that the limit of f of x as x approaches 5 is 7. So this part right here is 7. So now we add it to 3 times the limit of g of x as x approaches 5. So look back into the directions and it says that the limit of g of x as x approaches 5 is negative 3. So this part right here is, I'm going to bring that down, and then this part right here, as according to the directions, is negative 3. And so now I find my answer. So 7 plus negative 9. So my answer is negative 2. Voila, and that's it. So B, C, and D just kind of repeat. B, there's really nothing going on there. It is just whatever it says up in the directions. It's negative 3. C, so for f of x, it's 7. For g of x, it's negative 3. So the answer is negative 21. And then for D, the limit of f of x is 7. The limit of g of x is negative 3. And there's my answer. All right, example 4. So here we have to factor in order to actually find the limits. So once we factor and simplify, then we're going to use direct substitution. So for part A, this is the example I was talking about where direct substitution is impossible because if I were to plug in this negative 2 right here, I would get negative 2 plus 2, which is 0. Okay, and your denominator can never be 0. We can't divide by 0. It's impossible. So in case you've forgotten, this is a way that I tend to remember. So 0 divided by a number k, that's okay. But a number n divided by 0, that's no. You can't do that, okay? So a 0 in the numerator, that's okay. But a 0 in the denominator, that's not okay. Alright, so back to A. We're going to have to factor. So you take the top. Alright, so 3xy plus 5x minus 2. So 3 times 2, negative 2, is negative 6. I need two numbers that multiply up to negative 6, but they have to add up to 5. So hopefully you're like, okay, 1 and 6 are going to get me 6. And if I have 6 and subtract 1, if I have 6 and I subtract 1, I'll get 5. And 6 times negative 1 is negative 6. So x and x and plus, and then the leading coefficient here, or the number in front of the x squared, is a 3. So I'm going to have to divide these babies by 3. So far I'm just factoring, right? Okay, so let's see, this is now x plus 2 and x minus 1/3. But in the world of math, we don't leave the fraction. So what we do is we multiply these numbers by the denominator, which is 3. So I end up 3 times x minus 1/3 times 3, which is just 1. Or a shortcut, which is cheating because it's not mathematically correct, I say basically take the denominator and put it in front of that x. Okay, so I have now factored the top. So now the limit as x approaches negative 2, and now this is all factored out. So I rewrite the equation basically. You'll learn that with limits, you do have to continuously write limit, and then the x approaches whatever number, and then the rest of the equation until you've solved it. or basically until you start plugging in stuff. Okay, so this is my new equation now that it is factored. And I see that there's an x plus 2 on top and an x plus 2 on the bottom. So, by the laws of math, wonderful algebra, those can be canceled out. They just equal 1 now. And I am left with the limit as x approaches negative 2 of 3x minus 1 over nothing. It's beautiful. Now, you don't have to put divided by 1, right? And that's it. This is my new equation, and I'm going to take my new equation, and now I can do direct substitution. So this is the easy part. 3 times negative 2 minus 1, and that is negative 6 minus 1, so negative 7. And there's my answer. Now B, same idea. We're going to factor, and then hopefully direct substitute. If you look, I cannot plug in the 7, because if I do, 7 minus 7 is 0, and that's a no-no. Alright, so if you notice, the top is a difference, which means subtraction, right, of squares. X is squared, obviously, and 49 is essentially 7 squared. And if I simplify that, or rather, if I factor a difference of squares, I get x minus 7 and x plus 7. And that works great for me because the denominator is x minus 7. And so that is now factored. And then I do have to write the limit as x approaches 7. Okay, so I see that my x minus 7 in the numerator and the denominator, they totally cancel each other out. So now I have the limit as x approaches 7 of just x plus 7. And now I get to just plug in 7 plus 7 plus 14. Great, C. C looks slightly different only because instead of using x, we're using h. No big deal. And the cube. That's the only thing that's slightly different. So the best way to do this is essentially to expand the 1 plus h cubed. You want to actually write that out. So you can expand the 1 plus h quantity cubed just by good old-fashioned foiling, unless you actually know the formula for a sum of cubes. Let me just erase this here. And let's do it in red. Why not? Oh, I didn't erase. Okay, so whenever you have this, you can FOIL it out, good old-fashioned long way, or you could just use this formula. So it's a cubed plus 3 times a squared times b plus, oh boy, I hope I have enough space, 3 times a times b squared, I'll squeeze it in, plus b cubed. Now, in this case, I guess technically because of the way they wrote it out, this would be a and that would be b, but it doesn't really matter. Because of the plus, it's just a plus. It's not going to hurt anything. You could just switch them out. The h could be a, and the 1 can be b, because normally we do see it as h plus 1, right? So you could do that. Oh, oops. You could do that, or you could use FOIL. Okay, so after doing that, or foiling, and in case you don't remember, you have no idea what I'm talking about when I say FOIL. Gosh, I hope you do. But basically, you could just do this. You know, like 1 times 1 times h times 1, h times h, and then whatever you get from that, you'd multiply by the 1 plus h. These two things, the red and the green, they'll get you the exact same answer. And that is the purpose, right? Because math. Okay. Alright, so to keep everything straight, after doing one of these two techniques, I'm going to write down what you should get. So let me erase this. And I'll write it down in black. What you should get is h cubed plus 3h squared plus 3h plus 1. Okay, that's what you should get after cubing the 1 plus h. So, now I'm going to go ahead and write that out here because, yeah. So the limit as h approaches 0, and then the top is now h cubed plus 3h squared plus 3h plus 1. That's what we should have gotten. And then now minus 1. Right? That's still there. It didn't disappear. It doesn't, nothing in math magically just, I'm going to divide by h. Okay. So I need to simplify this somehow because I'm trying to solve this. I can't plug in the h equals 0 because then I end up with a 0 in the denominator. But I do see, oh look at that. The plus 1 and the minus 1, they cancel each other out because they equal 0 in the land of math. Limit as h approaches 0, so now I have h cubed plus 3h squared plus 3h over h. So I need to find something else. Something else I could possibly do here. I do see that they have something in common. Every single term in the numerator and every single term, well, the only term in the denominator, they all have h's in common. So I'm going to go ahead and factor out the h's. So from the top, this is now an h all by its lonesome that I have factored out from each term. See, h cubed has 3 h's. I took one, so now it's h squared. 3h squared had 2 h's, but I took one, so now it's just 1h left over. And then the 3h only had 1h to spare, but I took it, so now it has, or not has, but it has no h's left, and it's just a 3. So all divided by 0, I mean h, sorry. Okay, so voila, because math, well, because h divided by h equals 1, those cancel out, and now I have the limit as h approaches 0 of just h squared plus 3h plus 3. And now this is okay for me to do direct substitution. Plug in the 0, I get 0 squared plus 3 times 0 plus 3, which means my answer is just 3. Example 5, last but not least, rationalizing technique. Now the rationalizing technique usually involves something called, which I hope you remember, the conjugate. And we're going to use that in order to actually simplify these fractions into something we can use. Now the conjugate is the basic idea of multiplying a rational function by the number 1. The number 1's awesome. It could do anything, it could change anything into whatever you need it to be in order to solve. But I'm not literally going to be here and like, ooh, multiply by 1, because 1 doesn't actually work. Not that version of it anyway. What I need is the number 1, but it could look however I want, as long as it equals 1. Now rationalizing, see, I can't plug in the 0 into the x because I end up with a denominator of 0. So what I'm going to do is I'm going to multiply by the conjugate of the numerator. See the square root of x plus 1 minus 1? I'm going to use that term. I'm going to use the square root of x plus 1 plus 1. See, I just changed this little sign right here. I made it into a positive. Okay, so I'm going to multiply the numerator by that new number, which is my conjugate, but divided by, oh wait, I'm still in yellow, divided by, same thing, x plus 1 plus 1. Okay, see, because that right there, what does that equal? If I have the same thing divided by the same thing, it equals 1. And you can multiply anything by the number 1, because it doesn't actually change the equation, it just kind of changes what it looks like slightly, but it still equals the same thing. Alright, so now that I've done that, that's what I have to do in order to rationalize this function, because as it is, it's no good. No bueno. Can't do anything with it. Alright, so multiply. Let's see, I have the square root of x plus 1 times the square root of x plus 1. Well, isn't that interesting? When I multiply those two square roots, I just end up with x plus 1. And then the square root of x plus 1 times 1, and then, ooh, a negative 1 times the square root of x plus 1. Those are going to cancel out. Now, I'm not going to normally write these out. I'm going to write it out this one time. Okay? Oh, hold on. My computer, okay. So, as I was saying, I'm going to end up with plus the square root of x plus 1, right? So I've done this, and I've done this. So now I'm going to do this. So that's going to be a negative square root of x plus 1. And now negative 1 times 1 is negative 1. So that's the top. The bottom, don't go crazy multiplying that out. Just leave it how it is right now, because usually that's how you want it to be anyway. This is actually the way that you want to leave it, because it normally helps you out. And then, of course, I do have to write limit as x approaches 0. Just kind of have to. Okay, so I said I'm not going to write this normally because, look, these cancel each other out. Okay? So the limit as x approaches 0 of x plus 1 minus 1 over x. Ooh, looky, looky, these cancel out too. So now I just have the limit as x approaches 0 of x over x, which is, oh, look at that, it's 1 over, oh, I just realized I didn't write it on the top. Oops, my bad. Sorry. What I'm talking about is, yeah, this canceled out, but I guess I did it in my brain. I never wrote this part out. The rest of the denominator. That's still there. Okay, so 1 over x plus 1 plus 1, and that's it. It seems like a lot of algebra, but it's really not. And we had to do it in order to get something that we could use. Because now I have no problems plugging in the 0. I have 1 over the square root of 1 plus 1. I love 1. The number 1 rocks. Because the square root of 1 is 1. So 1 plus 1 is 2. And the limit as x approaches 0 is 1/2. Right, on to the next. B, same thing. Can't plug in the 0, so multiply this by the square root of 2 plus x plus the square root of 2. And then the square root of 2 plus x plus the square root of 2. Again, I'm multiplying by the conjugate, and this equals 1. We want it to, because the number 1 doesn't really change anything. Now, by using a special kind of the number 1, we can make the equation look different, but it still equals the same thing. Alright, so the limit as x approaches 0. Alright, FOIL. FOIL, people. The square root of 2 plus x times the square root of 2 plus x is 2 plus x. The factors, or the terms in the middle, if you remember right here, they always cancel each other out. And then negative square root of 2 times positive square root of 2 is a negative square root of 4, which is 2. Over x, and again, don't try to simplify this. Leave it as it is, the square root of 2 plus x plus the square root of 2. Okay, as you can see, the positive 2 and the negative 2, they cancel each other out. Again, the x's will cancel each other out, but I'll write it all out. See the limit as x approaches 0. I have now an x on top, an x on the bottom, and then I have this stuff on bottom as well. The x's do cancel each other out, leaving a 1 behind, right? Because x divided by x is uno. And then, let's see, I'll write it up again. Limit x approaches 0. Now it's just 1 over the square root of 2 plus x plus the square root of 2. Now I am able to plug in 0, but when I do, I end up with 1 over the square root of 2 plus the square root of 2. Please, this is not the square root of 4. It drives me crazy. Do not put the square root of 4, because that's wrong. It is 1 over 2 times the square root of 2, because how many square roots of 2 are there? There's 2 of them. Just like this was x plus x, that's 2x. So this is my answer. Now, in this class, you are not required to simplify. Okay, if this was algebra 2, this would not be a good way to leave your answer. Now, on the AP exam, might they make this a more simpler version? Maybe. And what I'm talking about is the square root in the denominator. Normally in math, they don't leave the square root in the denominator. They rationalize it by multiplying by a special case of the number 1, which is usually whatever the square root is. In this case, the square root is 2, so multiply by the square root of 2 over the square root of 2. And by doing so, I now end up with the square root of 2 over 2 times, let's see, the square root of 2 times the square root of 2 is the square root of 4, which is 2. So this is what I would end up with. Okay, but this is equivalent to this, which means they're equal. They equal the same thing. In this class, you are not required to go to this step. You can stay here, but it would be a good thing to know how to get here just in case you have to. Alright, and that's it. Answer the practice problems, please.